Bode plot is a frequency response plot. The plot is used to find out the stability of closed loop control system. This Bode plot consists of two subplots. One is a magnitude plot and it is a plot drawn magnitude versus frequency. The magnitude is expressed in log dB, decibels, versus frequency is taken on log scale. The second plot is a phase plot. This is phase angle versus again frequency, which is taken on log scale. And the magnitude plot is actually the y parameter is expressed in decibels in linear scale, but the frequency is taken on log scale, and that is the reason why this plot is drawn on semi-log graph sheet. So, any function, a system is represented by g of s into h of s, is a loop transfer function, and when this is given, the first step to draw the plot is you need to replace s by j omega, then the function becomes sinusoidal transfer function, and this actually consists of poles, zeros, and the gain constant. Generally, the system is represented by gain constant into numerator terms, they are called zeros, and denominator terms, they are called poles, some poles at origin, then non-zero poles. This is the standard representation in pole zero form of given loop transfer function. Now, as you replace s by j omega, the function become sinusoidal transfer function. Then when I say this is pole zero form, to draw the Bode plot, we need to have the time constant form. The time constant form is nothing but again some gain constant into 1 plus s tau 1 into 1 plus s tau 2 and so on, and again poles at origin into 1 plus s t p 1, 1 plus s t p 2 and so on. So, this form is known as time constant form. So, in order to draw the frequency response plot, that is Bode plot, the given loop transfer function must be converted, if it is given in pole zero form, into time constant form, and then we need to construct the plot. So, the various terms that appear in given loop transfer function, g of s into h of s is there will be a constant, then there will be pole at origin and number of poles at origin, where n is number of poles, and there may be a 0 at origin and there may be number of zeros at origin. Then the first order term like non-zero non-origin pole, non-zero pole or non-origin pole, and there may be non-origin 0, that is 1 plus s tau 1, and there may be a second order term. There may be a second order term also, that is generally called as a quadratic term. So, a given loop transfer function, it consists of several such terms, constant, then poles and zeros at origin and at non-zero location also, and there may be an quadratic term. So, drawing a phase plot is very easy in case of Bode plot, but the magnitude plot is slightly difficult because the magnitude is expressed in decibels. So, 20 log dB on y scale and frequency on log scale. So, we should have an idea of what will be the method to draw when you have a pole at origin or 0 at origin and pole at some other locations and all. So, you should remember one important term here. When there is a pole at origin, suppose the given function is pole at origin. So, as you know that pole is located at origin in S plane. So, what will be the magnitude plot for this? So, as this is a pole, it will have a slope of minus 20 dB per decade. If there is a pole at origin, the slope of the magnitude plot will have minus 20 dB per decade. The meaning of this, the slope changes at 20 dB per decade. Decade means the frequency is increased 10 times. That means, when I say the frequency is 10, then when frequency becomes 100. Okay. So, for every 10 times the slope changes at minus 20 dB if is a pole at origin. Similarly, if the given function is 1 by s square, then the slope of the line magnitude plot will have a slope of minus 40 dB per decade. So, slope changes at minus 40 dB for every 10 times the frequency changes. So, in general when it is s power n is number of poles at origin, then the slope of the magnitude plot for this will be minus 20 n dB per decade. So, pole will have a slope of minus 20 dB per decade. Now, if there is a 0 at origin, that means the given function is s, then it will have a slope of plus 20 dB per decade. Numerator term, the 0 in the given loop transfer function will have a slope of plus 20 dB per decade. In a similar way, in general, if you have number of zeros at origin is equal to n, then its slope is plus 20 n dB per decade. If there are 3 poles, then it is plus 60 dB, 4 zeros, then it is plus 80 dB and so on. This is for the case of poles or zeros at origin, then there will be a slope of minus 20 or plus 20 dB per decade. Now, let us consider the case of pole at non-origin, non-zero location pole. This is actually called first order term. So, the pole is at s is equal to minus 1 by tau 1, that is the meaning of first order term. Now, as you know that the term of this kind will also have a slope of minus 20 dB per decade, being a pole negative slope, but the magnitude plot for this function will be a 0 dB line for low frequency range, and the slope begins minus 20 dB per decade, and the point here, this is known as corner frequency 1 by tau 1 for this particular function. So, this is the frequency taken on x axis, and the magnitude is expressed in decibels. So, for all the frequencies, less than corner frequency, that is 1 by tau 1, the magnitude of the plot is 0 dB. The magnitude of the plot is 0 dB, and for the frequencies greater than corner frequency, that is 1 by tau 1, the slope begins. The slope begins at this rate minus 20 dB per decade. So, the meaning of this, suppose this magnitude, the value of the corner frequency here, this is actually 0 dB, and if the frequency is 10 here at 0 dB, then this will be minus 20 when frequency is 100. This is the meaning of per decade, that frequency is increased 10 times, the magnitude changes from 0 to minus 20. So, we say that it has a slope of minus 20 dB per decade. So, a first order factor denominator will have two approximate plots. One is 0 dB plot till the corner frequency, and minus 20 dB per decade plot after corner frequency, and both the plots meet at this point known as corner frequency. So, a first order denominator will have a corner frequency, and that corner frequency is equal to 1 by tau 1, which is to be determined from the given transfer function. Now, this plot, this magnitude plot is also known as asymptotic plot. It is nothing but an approximate plot. This is not the exact plot. So, if you construct the exact plot, the change in the plot is at corner frequency there will be a magnitude of minus 3 dB. That means the actual plot will be like this, So, this will be the actual plot which has some value at corner frequency, and for this pole it has a slope, it has a magnitude of minus 3 dB, and this plot is known as asymptotic plot or approximate plot. So, the error magnitude is given by actual value minus asymptotic value So, in this case it is minus 3 dB actual value, and this is 0. So, minus 3 dB will be the error if it is a pole located at a non-zero location. Suppose the given loop transfer function, we consider it as a open loop transfer function or loop transfer function, is having a factor, numerator term, it is also called as 0, and the value of the 0 at s is equal to minus 1 by tau 1. Then the plot is just reverse of the pole. That means this will have a slope, it starts at 0 dB, then at some point it changes with the slope of plus 20 dB because it is a 0, and the slope actually begins again at corner frequency here s tau 1. So, corner frequency is 1 by tau 1, and this will have a slope because it is a 0 at non origin. So, it has a slope of plus 20 dB per decade, and this also can be approximated into two plots. One is a 0 dB plot for the frequencies range less than corner frequency, and it is plus 20 dB slope it maintains for the frequency greater than corner frequency. In a similar way, this is an asymptotic plot we call, but the exact plot is different, and the value at corner frequency is plus 3 dB. So, this magnitude is 3 dB for a 0, and the actual plot looks like this. So, this will be the actual plot, and this is asymptotic plot or approximate plot. So, the magnitude at corner frequency for a 0 is plus 3 dB. So, the error if it is a 0, the actual value minus asymptotic value so it is plus 3 dB minus 0, so it maintains plus 3 dB for the 0 at non origin location. Now, if it is a quadratic term, that means second order expression. If it is a poles, quadratic term is in the denominator, then it will have a slope of minus 40 dB because second order term 20 into 2 40. So, minus 40 dB per decade, and the corner frequency of this term is undamped natural frequency itself. Similarly, if it is a term in the numerator, quadratic term in the numerator, it will have a slope of plus 40 dB, and the corner frequency is equal to undamped natural frequency that is obtained from the given function itself. Suppose the given function if there are two poles at different locations and the corner frequencies are 2 in this case because there are two independent terms. So, the corner frequencies are 1 by tau 1 and 1 by tau 2. So, the plot like it is a pole. So, every pole has got a slope of minus 20 dB per decade, and the plot magnitude plot for this, it actually start having a slope of minus 20 dB per decade, and this slope begins at some corner frequency 1 by tau 1, and there is a second corner frequency also. So, the slope of that particular term again minus 20. So, the net slope becomes minus 40. So, it actually changes at 1 by tau 2 at some other corner frequency, and the slope becomes minus 40 dB per decade. So, as there exist two terms and the magnitude plot will have two slopes, one is minus 20 dB per decade, begins at first corner frequency and changes from minus 20 to minus 40 at second corner frequency 1 by tau 2. How to determine the stability from the given Bode plot? So, for example, if you get the magnitude plot in this way, then there will be a phase plot, phase angle of the given loop transfer function versus frequency. So, for both the plots the frequency scale must be same, and say if you have got phase plot in this way. So, the characteristic equation is given by this. So, from this the loop transfer function g of s into h of s is equal to minus 1. This minus 1 can be written as minus 1 plus j 0, or this can be 1 at an angle of minus 180. So, the concentration to determine the stability of a given system in Bode plot is the magnitude of the loop transfer function is equal to 1, and the phase angle is minus 180 degrees. So, we need to identify 4 parameters from the Bode plot. One is GM, this is called gain margin, and second term is phase margin, these are margins like gain margin and phase margin considered as a stability parameters. What is the amount of gain that can be added to the system still so that system goes to the verge of instability. Phase margin is also defined in a similar way. Being a sinusoidal transfer function, it will have both magnitude margin and phase angle margin. So, how much gain and phase still you can add to the system, so that system goes to the verge of stability. Now, from this Bode plot, how to determine the gain margin and phase margin? Gain margin is determined at omega Pc, that is phase crossover frequency, and phase margin is determined at gain crossover frequency. Gain crossover and phase crossover frequencies are defined keeping 1 and 180 in view. So, gain crossover frequency from the plot is a 0 dB line, when the magnitude plot crosses the 0 dB line, okay, that point is known as omega Gc, because as I said magnitude is given by 1. So, 20 log 1. So, 20 log 1 is 0. So, whenever the magnitude plot crosses the 0 dB line, we consider that point as a gain crossover frequency point. Similarly, the phase angle plot. Phase angle plot, we should keep 180 degrees in view, say this is minus 180, and when the plot crosses, the phase angle versus frequency plot crosses minus 180, this is known as omega Pc. So, gain margin is determined at phase crossover frequency. So, that means from phase crossover frequency you should extend this onto the magnitude plot, say it cuts the magnitude plot at some point, measure that, okay, and this will be the gain margin. Similarly, from gain crossover point you project a vertical line onto the phase plot, and this will be the phase margin. So, gain margin at phase crossover frequency and phase margin at gain crossover frequency. The stability is this way defined, that in terms of omega Gc, okay, and omega Pc. So, the gain crossover frequency omega Gc should be less than omega Pc. We say that it is a stable system. If gain crossover frequency is less than phase crossover frequency, we say it is a stable system, and when omega Gc is greater than omega Pc, then it is an unstable system. So, the difference between this, if it is a stable system, you can add still some gain, so that system goes to the verge of instability. If it is an unstable system, you need to reduce the gain, okay, so that system comes to the verge of instability. So, if omega Gc is equal to omega Pc, there may be a situation that both frequencies are same. In that case, no margin can be added, gain or phase. So, we say that it is already at the verge of instability. So, it is marginally stable system. Marginally stable system, you can't add, you can't reduce the gain to that particular system when you have this situation, when gain crossover and phase crossover frequencies are same. So, keeping these three, we can say that the given system is stable or not. Look at this example. You are expected to find out the gain margin and phase margin. and the status of the system, whether it is stable or not, as it is the given system. So, this is the magnitude plot crossing the 0 dB line at omega gc, and this is the phase plot crossing the phase minus 180 degrees at omega pc. So, when to determine the gain margin, from omega pc, project a vertical onto the magnitude plot and see that what is the magnitude at this point. This is actually considered as gain margin, and from gain crossover point you are projecting it onto the phase plot, and this magnitude is minus 100 at omega gc. So, the expression for gain margin is negative of magnitude in decibels at omega phase crossover, and here this is what is the magnitude in decibels at omega pc. So, it is minus 40, so it is 40 dB. So, the meaning of this, still there is a margin of 40 dB. So, you can still add 40 dB to this system, so that system goes to the verge of stability. The meaning of that is, in this present case, when I say that system is stable in terms of the magnitude, then what is the phase margin? It is equal to 180 degrees plus the phase angle of the given function, at omega gc. So, 180 plus the phase angle value at omega gain crossover is minus 100. So, this is 80 degrees. So, both have positive values. Gain margin is 40 dB and phase angle margin is 80 degrees. Both are positive because the value of omega gc is less than omega pc. This is the requirement for stable system. I can say that system is stable for this particular function. Now, it becomes like when you add 40 dB at every point of the magnitude plot, then there may be a situation that becomes omega gc equal to omega pc. That means, this margin is when added to the magnitude plot, then a situation comes that omega gc equal to omega pc. So, that system is at the verge of instability. That is why this is being given that for this frequency it is a marginally stable system. The condition for the stability is omega gc should be less than omega pc. We say that it is a stable system because both gm and pm are positive, and when omega gc is greater than omega pc, it is an unstable system because both gm and pm are negative. When omega gc equal to omega pc, gm and pm are 0 because no margins. So, it is a marginally stable system. There may be a situation that the phase plot never crosses minus 180 degree line. So, in that case we can say that the omega gc is less than omega Pc, because omega Pc value is infinity because it is not crossing minus 180 degree line. So, we can say that the gain margin is infinite, because gain margin is determined at omega Pc, and omega Pc is the point when it crosses minus 180. So, if this situation comes when the phase plot never crosses minus 180 degree line, that system is absolutely stable system. Absolutely stable system, because the gain margin is infinity. And there may be a situation that phase plot maintains more negative than 180 minus 180, then omega Pc is 0, indicating that it is an unstable system. It is an unstable system. How to find the transfer function and the value of k from the given Bode plot? Magnitude plot is given to us, and how to find out the transfer function back. So, when you look at the plot here, this plot actually maintains slope of minus 20 dB from the magnitude m at frequency 1, and then it maintains the slope of minus 20 dB till omega 1 frequency. Then the slope changes here to minus 40 dB per decade. That means a pole is added to the existing pole, and this minus 40 dB is maintained up to next corner frequency omega 2, and you can see now the net slope becomes minus 20 from omega 2. So, minus 40 now has become minus 20, and at omega 3 again it has become minus 40. So, the magnitudes are given at omega 1 frequency it is 24.1 dB, and at omega 2 minus 12.5, and omega 3 minus 200.5 dB is given. This is the data given. So, the question begins like this: we need to determine omega 1, omega 2, omega 3, they are known as corner frequencies. You need to determine them, and also the magnitude m, what is the magnitude, and the corner frequencies. So, with the help of these 4 parameters, we can find out the transfer function of this particular plot. So, you can actually see here, I would like to determine omega 1 first. So, to determine omega 1, consider this portion of the plot which maintains the slope of minus 40 dB. You can consider this as a right angle triangle. You can consider this as a triangle, and this line has a slope of minus 40 dB. So, there is a formula for the slope. M is the slope. So, it is equal to y2 minus y1 by x2 minus x1. If you have coordinates x1 y1 and x2 y2, then slope is given by this one. So, you have 2 parameters here, 2 parameters here, and the slope is actually given minus 40. So, m is minus 40, okay, and the value here, the magnitude is 0 dB, minus 24.1 magnitude here, they are y coordinates, and the x coordinates log, because it is taken on log scale, log 8 minus log omega 1. So, this is the expression to determine the omega 1, which is known as corner frequency with the help of the slope expression, a mathematical expression, and from this the unknown is omega 1. So, log 8 is 0.9. So, it becomes minus 36.12 plus 40 log omega 1 is equal to minus 24.1. So, from this you can actually get omega 1 as 2 radians per second. So, omega 1 is 2 radians per second, which is obtained from this slope expression, and you can see that you can cross check that whether it is a right answer or wrong, because here it is a 8 radians per second and here it is 1. So, definitely this is 2. So, it is in between 1 and 8 and you got 2, probably it is right. So, once you got omega 1 2 radians per second, now I will try to find out m. M is the magnitude, okay, at frequency 1. Again I use the same slope formula because this line maintains a slope of minus 20 dB per decade. So, minus 20 is equal to y coordinates. Y coordinates 24.1 as y1 or y2 minus y1, which is unknown parameter, by x2 minus x1. Now, I know the value of omega 1. So, log 2 minus log 1, which is given in the problem. Okay. So, from this you can actually get the slope, the value of the magnitude in decibels, 30.12 dB. So, in order to determine the magnitude, I need to know omega 1. That omega 1 is obtained first, then the magnitude is given by 30.12 dB. In a similar fashion, we need to determine omega 2 and omega 3. They are the next corner frequencies. You can see here omega 2 and omega 3, they are also known as corner frequencies. So, for omega 2, you need to consider this one. So, what is this slope? This slope is again minus 40. The slope is minus 40. So, to determine omega 2, minus 40 is equal to minus 12.5 minus 0 divided by log omega 2 minus log 8. Minus 40 is the slope that is maintained from 8 to omega 2, and the magnitude at omega 2 is given minus 12.5. So, y2 and y1 is 0, and log omega 2 is unknown and log 8 is known. So, from this again we need to determine omega 2, and this value is 16 radians per second. 16 radians per second. Now, for omega 3, I need to use again the slope expression. The slope here from omega 3, we can see this is the slope from omega 2 to omega 3 minus 20. The slope has become from minus 40 to minus 20. So, minus 20 is the slope m. Okay. Now, you know these two coordinates, minus 200.5 as y2 minus y1. y1 is minus 12.5 divided by the unknown parameter is log omega 3 as x2 coordinate minus log omega 2, and this omega 2 value is calculated as 16 radians per second. The only unknown here is also omega 3, and that omega 3 is 40 radians per second. So, this is the way we should determine the corner frequencies of the transfer function omega 1, omega 2 and omega 3 from the basic expression slope is given by y2 minus y1 by x2 minus x1. So, we could determine m value in decibels 30.12 and all three corner frequencies are determined. Now, how to obtain the transfer function from this data? We have got the values of corner frequencies omega 1 as 2 and omega 2 as 16 and omega 3 as 40 radians per second. Now, the magnitude in decibels at this frequency, you have got 30.12. Now, how to write the transfer function? The transfer function is nothing but the g of s into h of s, the loop transfer function. It generally consists of k and zeros and poles. Now, when you look at the magnitude plot, will there be any zero in the given system? When you look at this portion of the plot, it is minus 20 dB per decade. So, it is definitely a pole, because pole will have negative slope, 0 will have positive slope. So, this is a pole with a slope of minus 20 dB per decade. Now, you can see this is a corner frequency omega 1. Here the slope has become minus 40. That means another pole is added to that. So, the slope has become minus 40. It is continued and at this frequency the slope has become minus 20. That means minus 40 to minus 20. So, what should have been added here? Minus 20 to minus 40 means a pole is added, no doubt, but when it is minus 40 and it is becoming minus 20, definitely a 0 is added, because minus 40 becomes minus 20 only when minus 40 plus 20 is equal to minus 20. So, that way I can say that the 0 is added here with the corner frequency of omega 2. So, you can have the numerator term 1 plus s by 16, where 16 is the second corner frequency omega 2. So, a 0 is added at this corner frequency. So, the slope has become minus 20. Now, in the denominator, it is very easy that the slope begins at this point with minus 20 dB. So, no corner frequency for the first point. So, I can say that it is minus 20 dB. So, it is only one pole at origin. If this is minus 40, then I should have written s square here. Now, the second term at omega 1, the corner frequency is omega 1 equal to 2, slope has become minus 40. So, 1 plus s by the corner frequency, where the slope changes from minus 20 to minus 40. So, 2 is the corner frequency. At this point, the slope changes to minus 40. So, second pole is added. Now, it is continued. Then a 0 was added here to become minus 20. It is already added. Now, at this omega 3, the slope has become minus 40. That means another pole is added to that, and it is corner frequency of 40. So, 1 plus s by 40. So, this is the way that a transfer function is obtained with the help of corner frequencies 2, 16 and 40 we should able to write. Now, the another important thing is we should find out the value of k, that is not obtained here. So, we know that the magnitude is m, the magnitude m is equal to 30.12, the magnitude of the transfer function at frequency 1 radian per second at frequency 1 radian per second, we know the magnitude is equal to 30.12. So, that is equal to k into 1 plus j omega by 16 by j omega, replacing s by j omega, 1 plus j omega by 2, 1 plus j omega by 40. Now, that omega value, the magnitude m 30.12 is at 1 radian per second. So, substitute omega equal to 1 in the magnitude part. So, and this function equated to 30.12 and substitution of omega equal to 1 radian per second, it gives the value of k as 32. So, the gain constant is 32 and that is obtained from the given Bode plot. So, now I can write that the given transfer function, loop transfer function from this plot is 32 into 1 plus s by 16 by s into 1 plus s by 2 into 1 plus s by 40. This is the way we should obtain the transfer function from the given Bode plot.